Happy Thursday. We see the light at the end of the tunnel. But it could be an oncoming train. We just don't know yet, right? Green's theorem. First of three in vector analysis that we study, and this is the crux of the calculus sequences, these three theorems. So everything that you've done for the past year and a half has led up to this. D is a domain whose boundary is a simple closed curve oriented counterclockwise. F is a vector field, two-component vector field, F1, F2, whose component functions, whose components have continuous partial derivatives in an open region containing our domain. Then the circulation along the curve del D of f dot dr is the double integral over the domain D of partial of f2 with respect to x minus partial of f1 with respect to y. Makes that square problem we did much easier. Because then instead of having to do the four paths, that path was a simple closed curve enclosing a region D. We could have just done double integral over that domain, which was what, 0 to 1 cross 0 to 1. We are going to verify Green's theorem. Our vector field, xy plus y squared, comma x squared. Gonna make notes. Right, f1 is xy plus y squared, f2 is x squared. C is the curve of the region bounded by y equals x and y equals x squared. And we can assume a positive orientation. Right, that point is obvious. It's the origin. What's that point? What's their point of intersection? That's one coordinate. I want the ordered pair. You overthinking it?
One.
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 And x is one, y is one. We'll label that D. From that, you can easily see that C serves as the boundary of D. Right, verify Green's theorem means we have to calculate both the path integral and the double integral and show that they come out to be the same. Let's start with the line integral. We need to parameterize this. Our path can be broken down into two paths. C1 we're going to say is 0, 0 to 1, 1 along y equals x squared. Right, so that is that branch there. Right, call this then obviously C2. All right, so that's the path 1, 1 to 0, 0 along y equals x. Parameterization for C1. Gonna be what? Parameterization is 2 components. So t-square is that can be your x component or y component?
Y.
What's your x component?
T.
And what is the domain? The valid parameterization? What about C2? By that.
Can you go more in depth on how you got C2 or well the R vector? I'm a little bit confused.
Oh, man.
Anybody?
I mean, you're the one who gave it to me, so.
So what I did is I made a first point at 1, 1. So I started it for each of them at 1. And then since we're going down to 0, 0, you're going down at like -1, like each step. So I made each one give it 6.
Okay.
So that when you would plug in values from 0 to 1, like if you plugged in 0, it would be 1, 1. And if you plugged in 1, it would be 0, 0.
Okay, that makes sense. Thank you.
So
Could you also do T for both of them and have it go from 1 to 0 and have like a negative integral and flip the?
Yes.
Okay.
Right, you could also do that. Set C, actually, you don't even need to go 1 to 0. You can set C2 to be 0 to 1, but realize that you oriented it in the wrong direction. So then you have to multiply it by a minus. That also works.
So just to like reiterate what he said, just make sure I got that right. You could make it T and T and then have it from -1 to 0. Then
So what you can do is think of it this way. Orient it in the red direction, which would be T goes from 0 to 1. But that's the opposite orientation of what we want. So then you just multiply the integral by -1.
Okay.
That would also be valid, which is the same thing as instead of going T 0 to 1, you'd say T goes 1 to 0. Right, but that just looks weird. But that is also a valid method. You'll get the same thing, right? Right, so remember, if you can write your path as the union of non-overlapping paths, then your path integral is just the sum of the individual path integrals. For C1, we said t is going to go 0 to 1. Evaluate the field over the parameterization. X becomes t, y becomes t squared. Sorry, that's t to the fourth. Dotted with r prime dt. C2, t went from 0 to 1. Both x and y become 1 minus t. Now dotted with r prime. Dt. First integral should become t to the fourth plus 3t cubed dt. Second integral, we're going to get a negative. And then it should just be 3 times the quantity 1 minus t squared dt. Fifth t to the fifth from 0 to 1 is a fifth. And 3/4 t to the fourth from 0 to 1 is just 3/4. The antiderivative of 3 times 1 minus t quantity squared would be negative 1 minus t quantity cubed. Right? You could also expand out the 1 minus t squared. That's fine. But change a variable I find to be easier. One minus t cubed evaluated from 0 to 1. At 1, it's 0. That's negative 1. Fifth plus 3/4. 19/20. Minus 1. Negative 1/20. Which of course automatically means this cannot be conservative. Right? Conservative vector fields have a circulation of 0. Speaking of that, before I do the double, would this theorem still be valid for conservative vector fields? In other words, does this theorem satisfy that a conservative vector field has zero circulation if you're to use the double integral?
What was the question again?
Look at that double integral. If f is conservative, would that be zero? Why?
Just,
Math doesn't care about feelings. Call it what you will, it doesn't care. You're overthinking this. The answer is obviously yes. If f is conservative, then those partials are equal. Mixed partials are equal in conservative vector fields, which means you're actually just integrating zero, which is zero. So this doesn't violate the fundamental theorem of line integrals, which is good. If it did, we'd be in trouble. Something else to point out with Green's theorem. It's only valid for circulation. If I give you a path that is not closed, you cannot use Green's theorem. Right? The path has to be closed. So how do you want to describe the region?
Is it y equals x minus y equals x squared?
This doesn't make sense to subtract two equations. Think back to double integrals. There are two ways you could describe the region. Ooh, I'm definitely looking forward to my office hours when I start grading your third test then. That'd be one description. The most obvious description. The other one, y would go 0 to 1. X would go y to root y. Partial f2 with respect to x. 2x. F2 is x squared. Partial f1 with respect to y. 1 plus 2y. I think I'm going to write it this way. Oh, nope, I can't. I'm doing y first. Glad I caught it now. There's a mistake up there.
The integration for BF1 should be x plus 2y.
For some reason I wrote y instead of x. This feels like a Monday morning instead of a Thursday morning. Y evaluated from x squared to x would be x minus x squared, right? That's going to be times x. X squared minus x cubed. Then we get minus y squared from x to x squared. So minus x squared plus x to the fourth. So integral 0 to 1 x to the fourth minus x cubed dx. Be 1/5 minus 1/4. Which is negative 1/20th. Bless you. Well, look. This was the line integral is equal to negative 1/20th. Double integral is negative 1/20th. Green's theorem has been verified. If I really wanted to, I could make the final 3 questions that would incorporate the entire semester. Verify each of the 3 theorems. That would literally cover everything we've done all semester.
Like the difficulty rating would be on that.
Well, let's say I have done it before.
Let's say our shoes, not yours.
Well, I mean, I've done it for a class before. I'm trying to remember what they got. One student turned it in blank and then said, this is what happens when you don't take notes. So. Several people didn't read it and only did half the problems. They only did one direction. They didn't actually verify it. The ones who actually did the work all passed with like a B or an A. So not that difficult. Because I wouldn't make like the fields or the curves or anything like extremely difficult. That would kind of defeat the purpose. If I did make the curves extremely difficult, yeah, you'd probably be working on it for the entire week. Maybe longer. I probably won't do that. Final will be a good mix of topics from the units. Depending on how the random number generator is feeling at that particular moment. If it picks all easy ones, then you could get something stupid like, oh, here's this multivariate function. What's its domain? Right, that's 10 points.
That'd be really cool.
Then again, it could give you something hideous. All right, evaluate this triple integral of this nasty looking region. That requires you to do like 3 trig subs or something like that. So as I said, it just depends on how the RNG gods are feeling at that particular moment. I'll be writing your finals either tomorrow or next Monday. I'm looking forward to that.
There will be a 4th exam happening.
There's a 4th test, yeah, that'll be coming up. I already have that written.
Right. That's slated to be happening.
As soon as I finish divergence theorem. Or Stokes theorem, depending on which one I do first. Next Tuesday. Why is that a circulation when it's clearly not. Oh, you are. Equation. Do that one, okay. What's going on? Okay. Why is it being weird? I think this is what I'm gonna have to do then. That's what I have to do, yes. There we go, now the problem's right. Notice that this path is not closed. That means we can't use Green's theorem. So this is just straight up a line integral. Oh boy. Parameterizing that path should prove very interesting. Unless you recognize that that vector field is conservative. Because it is. Which means this now becomes a fundamental theorem of line integrals problem. So you have your choice. You can either try and parameterize that path, or you can pick another path that goes from 0, 0 to 2, 1. Or you could try and find a potential function. Doesn't matter, all the same. Least amount of work might be trying to just parameterize the straight line from 0, 0 to 2, 1. I should get. Actually, would it be less work? So I can do what? 2t. On the t. That'll work. T goes 0 to 1. The 160 t to the fourth minus 40 to the fourth. Then we get negative 12 t to the fourth. Dotted with 2, 1 dt. (160 minus 4, 156. 156 times 2. 312. Plus. No, minus. Minus 12t to the fourth. Perfect. Gives you 60. Which is what I got by finding a potential function. I think that was less work. Right, because remember, conservative vector fields, the path does not matter. All that matters is your starting point, your ending point. So if you're given, if you actually plot this curve, it's actually not a hideous curve. That's the curve. So the path isn't hideous, but trying to parameterize that is. But that's okay, because it doesn't matter. So we can just take the straight line from the 2 points, or any path between the 2 points.
It wasn't closed. We just look for something, maybe it was simpler, like maybe it's conservative, and that would make it.
Yes. Right, if it's not closed, so if you have a path integral, always check to see it's conservative, because if it is, you can choose a simpler path. Unless I specifically say you cannot use the fundamental theorem of line integrals. Because I think I did do that on one of the problems on the test. Otherwise, yeah, just try and find a simpler path. If it's conservative.
So F is path independent because it's conservative.
Yes,
Okay. What does that necessarily mean, path independent?
the path doesn't matter. Right, look at the curve that I used. That is definitely not that curve. Right? This is the actual curve.
Yes.
That is not the path that I used. I used a simpler path. And I can do that because it's path independent. All that matters is your starting point and your ending point. So any path from 0, 0 to 2, 1 gives you the same result.
So you can do that anytime.
It's conservative.
Path integral.
The vector field is conservative,
Vector.
which means it's path independent. Right, that's kind of the idea behind trying to find the potential function. But usually just doing a straight line is a lot less work than trying to find the actual potential. So it just all depends. Oh, by the way, since most of the force fields you deal with in physics are conservative, a lot of the physics integrals, you can just do path independence. So if the area bounded by a simple closed curve C is given by f of the circulation of x dy minus y dx. So C is a simple closed curve. It's enclosing a region D. So we can use Green's theorem. Be the double integral over that region. Partial x of x minus partial y of negative y. Okay, do not be fooled by the order in which it's written. F is not x comma negative y. It's negative y comma x. That's 1 minus negative 1, isn't it? You get 2 times the double integral over d. Which is 2 times the area of d. Solving for area, you get 1/2 that circulation as desired. This is now a third way of finding area of a region. Right, first way was Calc 1. Second way was the double integral dA. Now the third way involves circulation.
And that, don't be confused by the order because dy comes first and dx. It's still that partial x of f2 minus partial y of f1.
Right.
Where's the switch that you described?
You may take this to be F1 because it comes first.
Be f1?
X. Up here.
Oh,
Because it's written first. But it's not. That's F2. Right.
okay.
So don't be confused by the order in which we write it. You look at the differentials of a term in F1 and F2.
Right.
Right, because I could write it in any order I want. And that's especially true when we get to Stokes' theorem and it's dx, dy, dz. I could write dz first, then dx, and then dy. And you just have to remember F1 is always attached to dx, F2 is always attached to dy, F3 will always be attached to dz. So now we can go ahead and find area of parametrized regions or parametrized curves. In this case, the ellipse. If A is greater than B, then this is an ellipse with semi-major A and semi-minor B. If B is greater than A, then this is the ellipse with semi-major B and semi-minor A. It just depends. Does it stretch out longer on the x-axis or the y-axis? Here it's arbitrary. Doesn't matter. Right, but now instead of trying to do it geometrically or trying to set it up as a double integral, right? So trying to parameterize or trying to describe the region in polar or rectangular, which is hideous. Right, we're gonna just do it using closed path integral.
I lost you when you were talking about the major and minor. So which one?
Major is so the major axis is the one that it's longer on.
When A or B is
Right, so if A is larger, then it's longer on the x-axis.
On the X.
So your major axis is the x,
Right.
and your semi-major is A. It's where does it extend out to? What point on the x-axis does it extend out to? Right, so the major is always the longer one. The minor is then the, I guess, squished. And keep in mind, the major axis doesn't actually have to be the x-axis, right? Because if you shift the center, the major axis is now whatever that passes straight through the center, the longest one. So in that case, it would be, if A is large, it'd be x equals or y equals whatever the shift was. Right, let's say it's centered to HK, it'd be y equals h would be your major axis. All right, so remember, area is half the circulation, x dy minus y dx. 1/2. What would the parameter domain be? One half the integral from 0 to 2 pi negative b sine of theta, a cosine of theta, dotted with the derivative of a cosine theta, b sine theta. D theta. Bless you. Oh, what am I doing? For some reason I thought there was only one negative. No, it's two, so that is positive. You don't say this can't be right. I was going to get a 0 out of that. Just get a half integral 0 to 2 pi of AB. Which equals pi times A times B. Which is the geometric formula for area of an ellipse. Proven using calculus now. Go ahead and evaluate this circulation. So look at that triangle. Look at that path. Is that a simple closed curve? Where? Yes. So is that path simple closed? It is. It's clearly closed. Simple just means it's non-intersecting. So the path doesn't intersect with itself. Laminus, I think is what it's called, the infinity symbol, that is not simple, but it's the union of two simple. That means we can use Green's theorem. Call the region that encloses D. Partial F2 with respect to X is negative sine X. Partial F1 with respect to Y is 1. I'm gonna go negative. I'm gonna factor out a negative because you have negative sine X and it's gonna be -1. We need to describe the region D. If we go dy dx, x goes from 0 to pi over 2, y goes from 0 to 2x over pi. Now notice this is oriented in the positive direction, right? So I don't have to worry about multiplying by a -1 at the end. One. The 1 is on there. Yeah, that is on there.
Oh. Circle and nothing.
Zero to pi over 2. Two over pi x sine of x plus 2 over pi x. By 37, formula number 37. That antiderivative, we get 2 over pi sine x minus x cosine of x. And then obviously that second one, 2 over pi times x is simple, x squared over pi. Evaluate that from 0 to pi over 2. negative 2 over pi plus pi over 4. Questions on Green's theorem? That's what this line is. All right, you have to find the equation of that line. Of this line right here. All right, so it has a y-intercept of 0. It has a slope of 2 over pi. Right, because it goes from 0 to 1 along the y and then 0 to pi over 2 along the x. So it becomes 1 over pi over 2. So that's how you get y equals 2 over pi times x. Well, I'm not plugging anything in for dr. I'm using Green's theorem. Well, you could try and you could try and do the path integral if you wanted to, but you'd have to break it down to 3 paths. So rather than do that, I decided Green's theorem is the best choice. So much fun, I lost track of time. It's 10:40. So what we will do is tomorrow start off with the quiz on Green's theorem. Then we will do either Stokes or divergence. I haven't decided which one I want to do first. Divergence is definitely easier, but Stokes is an extension of Green's theorem. But it's the problem child of the group. So that is the plan for tomorrow.
Where's at the end?
Depends on how much time we have.